never decreases the likelihood function. So it either increases the likelihood function or doesn't change it. And today we are going to discuss an application for this for estimating the parameters of a mixture of Gaussian model. And after that we continue with another unsupervised learning algorithm, namely the principal component analysis algorithm or algorithms. Any questions? Any questions about the proofs we did last week? So everything is clear so far, good. So just to recap very briefly, this is what we did, that we had a data set x1, x2, xn. We have some unknown variables. For example, in clustering, these unknown variables were y1, y2, yn. They just indicate the cluster label. And in the mixture of Gaussians, we had parameters mu1, mu2, mu_k. They are the means of the clusters. Pi1, pi2, pi_k. They are the prior probability distribution of the clusters. And sigma1, sigma2, sigma_k. They are the covariance matrices of the Gaussians. And our goal is to design an algorithm that can do a maximum likelihood estimation in this model. That is, we want to maximize the log likelihood in theta, and if we have n instances, then our estimate is theta hat n. And the EM algorithm, how it works, that first you create a Q function that has two arguments, theta t minus 1 and theta t. And what you do, that you take the log of the joint density of the hidden random variables y. So they are the cluster labels in our case. And we have the data. Those are the x's. And given the parameters at time step t, this is so you take the expected value of this log likelihood with respect to y. And the posterior distribution with respect to y is this. So in this posterior distribution, you use parameters at time step t minus 1. So you create this Q function, which depends on theta t minus 1 and theta t. And so that's the E step. And in the M step, you just use this Q function, and you maximize this in the first argument. So it's Q theta t minus 1. You maximize this in theta, and that will be theta t. And then in the next iteration, you put theta t here to the second argument, and you continue this iteration. And we discussed that, or we proved that if you do these steps, then in the next step, the likelihood function is either bigger or the same as the likelihood function at time step t. All right, and we discussed this intuition behind the EM algorithm, that you have the likelihood function, that's this black curve. X-axis is theta, and what the EM algorithm does, that it lower bounds this function with another function called free energy. And in the E step, you try to minimize the gap between this free energy function and the likelihood function. So you move this free energy curve up till it touches the likelihood function. It's always smaller or the same as the likelihood function. And then you maximize the free energy function. And then in this maximum point, you fit a new free energy function. Again, you push it up till it reaches the likelihood function, and you do this iteration. So that's the EM algorithm. The variational method, in the variational methods, you can even generalize this framework even further, where you just do a partial step. That is, your free energy function will not necessarily touch the likelihood function. You just try to optimize this up till it gets close. And in the optimization, when you do this optimization, you always assume that the Q distribution function that we used, it's in a tractable form. So sometimes, depending on the model in the EM function, we had this Q function we optimized, right? This py given the data and theta t minus 1, it might be intractable. In the variational approach, you replace this with another function that's close enough to this, but it's in a tractable form. So those were the main ideas. And now let's see an application for this model. All right, so let's come back to this mixture of Gaussian case. So we have unlabeled data x1, x2, xn. We know that there are k classes, so that's known. And for simplicity, let's assume that we know this prior distribution pi1, pi2, pi3, pik. And we know that the Gaussians have a common variance sigma squared. And what we don't know is the mean vectors of these Gaussians, and we just want to estimate them. Okay, so this is just the first step. Ideally, what we want is that, so after we solve this problem, we'll discuss how to generalize this even further, where you don't know pi's, and you can even assume that there's a covariance matrix sigma I for each Gaussian, and they can be different. All right, but for now, we just start with this simple problem. Okay, so we want to solve this parameter estimation problem. So we want to estimate mu1, mu2, mu_k using the EM algorithm. And we already know that the likelihood function, that is the probability of x1, x2, xn given the parameters. We have IID observations, so it's the product for all j1 to n. And if you do Bayes rules, then we will see that this probability is nothing else, just proportional to the product of this sum, where you sum for each cluster from 1 to k, and this is the Gaussian distribution, and this is just the probability of the Gaussian components. Okay, so we calculated this many times. So this is just the likelihood function. Our goal is to maximize this in mu1, mu2, mu_k. Any question about this? Okay, so this is what we want to do. And we want to solve this problem with EM. So first we create a Q function. So what was that Q function? You remember we need to, let me come back to that. Here we are. So in the EM algorithm, we need to create a Q function, theta, say theta t, and this was just the expectation of this posterior distribution So this is the posterior of y, and I want to calculate the expectation of log p y, the data given parameters theta, and that's it. So this is the Q function. So this is the E step. So let's see how this Q function looks like for the mixture of Gaussian case. All right, so in our case, Q, say theta t and theta t minus 1. So we need to calculate this expectation, and this expectation is nothing else, just the sum, because we have IID samples x1, x2, xn. So sum from, I use j. J goes from 1 to n. And the probability of y given the data and parameters that let me use t minus 1. T minus 1, so it's sum from I to k. So in our case, I don't use integral because the y's, we have discrete number of y's class label. So I replace this integral with a sum, and these probabilities are discrete probabilities, right? So py given the data and parameters at theta t minus 1 is just, I can write that this probability that class label of instance j is, say, I, given the data, which is x1, xn, and given the parameters theta t minus 1. All right, and this is actually nothing else, just the probability that the instance, the cluster label of instance j is I, given, so I need to know only xj, right? Because the others, x2, xn, it's independent from the cluster label of the instance j. It's theta t minus 1. Okay, and what's theta in our case? I just want to estimate the parameters mu1, mu2, mu k. At time step t minus 1, t minus 1, t minus 1. Okay, so this is this probability here. And now if we use Bayes rules, so the probability of y given x is proportional, using Bayes rules, the probability of x given y times the probability of y. Probability of yj is I is, according to our notation, is pi I. And we assume that it's known. The probability of xj given yj is I, and these parameters, we know it's a Gaussian with mean mu I t minus 1. And we assume that sigma is known. So this expression is proportional to this quantity. Okay? Which means that these probabilities, because they have to sum to 1, it's exactly just this quantity divided by the sum from 1 to k. This quantity divided by itself, but you need to sum from 1 to k. Okay, so we can calculate these probabilities. Any question about this? It's crucial that you followed this. Who got lost? Who followed me? Who's sleeping? All right, so the point is that we can calculate these probabilities, and in the E step, that's what we need. To create this Q function, we need these, to know these probabilities. Okay, and that's the E step. We calculate these quantities. So given parameters at time step t minus 1, we can calculate these probabilities. Because the data is known, we assume that pi is known, sigma is known, we are done. Yes?
Why is sigma known?
Oh, that was our assumption. We know sigma squared, and we know the pi's. To simplify our life. Later we can discuss what you can do if they are not known. But just as a first step, we assumed they are known.
Isn't there a log term in the Q function that we have to deal with?
So this log?
Yeah.
Right, so we just calculated these probabilities.
Right.
And to create this Q function, we need these probabilities, and then you can plug these probabilities here. And then we are done.
But what happened to the log term?
To this right guy?
Yeah.
Right, so we will go there. Yeah, next slide. Okay, so this is the E step, and then in the next step, the M step is that you calculated this Q function, and you need to maximize this Q function in theta t, right, in this expression. And that's what we are going to do. Okay, so again, Q function, we just calculated these probabilities, and then we start discussing what you just as the next this term. So this is the log of the joint probabilities given parameters at theta t. And I can rewrite this that the log of x given y plus the log of y's given theta t. And this time, to simplify our life, we assume that these are known, phi I. And this is a Gaussian distribution with parameters mu I t. And this is what we want to, this is where we are going to maximize, right? In the M step, you maximize here in theta t. And these quantities we already calculated in the previous slide. Okay, so the joint distribution is pretty simple. And these probabilities, we just calculated them in the previous step. And just to simplify our life, let's introduce a notation that these probabilities that we calculated in the E step, let they be denoted with Rij t minus 1. So t minus 1 because we just use parameters at time step t minus 1. And it depends on I and j. So it's Rij t minus 1. This is just this conditional probabilities of the cluster label wise. Okay, so we calculated this in the E step. We need to plug them into this form in the M step, and then we need to maximize this in mu I t. All right. So we need to maximize this Q function in mu I t, and if you look at this expression again, it's just the sum from j goes to 1 to n, and there's a sum here from I to k. You cannot see it because I wrote it with white. It's there. So from sum I goes to 1 to k, Rij t minus 1, this expression times this. Oops. Right, so let me correct this indeed. So there's a tick point. So there should be a sum. I goes 1 to k, and there should be a x function here.
Probably you don't need x because you are taking the log as well. The log likelihood, the proportion is close to it.
Oh, right. So the log x they cancel out. So I don't need that. Very good. And we will see why I don't need this other sum either next. All right. No, maybe I just delete this sum. So Right, I just wrote 2 steps in 1 step. That's the confusion. So here is this Q function, and let me write it here. So Q theta t given theta t minus 1. This is sum j is going from 1 to n, sum I is going from 1 to k, and then r I j t minus 1, and then we don't need the x because of the log, and then minus 2 sigma squared xj minus mu I t squared. Alright, so this is where we are. We want to maximize this in mu 1 t mu k t. When I maximize this in mu I t, then because of this sum, so if I want to maximize this expression in mu I t only, then I just need to maximize this expression sum j from 1 to n. And because of this sum, I can just focus on the i's term, which is r I j t minus 1. xj minus mu I t squared, right? So that's why I don't need this sum here, because I just maximize in the ith term, and in the sum, the ith term is independent from the j's term.
Can you go a slide back?
Back 1 slide.
Why do you write that sum on the bottom? Can you just ignore it because that doesn't depend on j?
So once again,
Like, does that sum on the bottom? Yeah, that you're pointing at before. That sum that doesn't depend on.
this is r I j.
Yeah, Rij t minus 1.
Yes. Okay.
It doesn't depend on yj, right?
It depends on I and j. J I t minus 1.
The sum on the bottom. That's just for any y.
Oh, the sum. This sum doesn't depend on I.
You can just ignore it, right?
Yes. The sum doesn't depend on I.
Can you also cancel the pi? Or?
The pi's not really, because
Oh, that's okay. It's okay. Yeah, forget it.
okay. So this is Rij t minus 1.
Thanks.
And then the point is, if I want to maximize this Q function now in mu I t, then I just need to maximize this expression here. That proves us here. Questions? Any question about this? No. So then how can we maximize this in mu I t? Well, we just calculate the derivative and check when the derivative is 0. And that's very simple, right? So what's the derivative of this with respect to mu I t? It will be the sum Rij t minus 1 2 times this expression. I can even forget about sigma squared because it's just a constant, times xj minus mu I t. I'm just interested when it's 0, and I need to solve this for mu I t. And if we do that, then we have that mu I t Right? So we have sum j goes from 1 to n ri j t minus 1 times xj. This is equals sum j is going from 1 to n ri j t minus 1 mu I t, and from this mu I t is just sum j is going from 1 to n ri j t minus 1 xj divided by this expression. J is 1 to n ri j t minus 1. So this is what we have here. Then mu I t is just the weighted linear combination of xj's with these weights. And again, just using, if you remember the Rij definition, these were just the posterior probabilities of the cluster label-wise. And that will be our new mu. Okay, so this is how you update the mean vector in the mixture of Gaussian model. You have this new mu. Using this new mu, you calculate again new weights. You have new weights, you have new mu, and so on, and you do this iteration. Okay, yep.
Explain again, how did you actually get rid of the second sum?
Second sum, this one, right?
Yes.
Right, so that's what's here, that this is my objective, and if I want to maximize this in mu I, then where can I see mu I? So I can only see mu I in the i's term. So you have a sum, and only the i's term of the sum depends on mu I, so you can get rid of the others.
Okay.
Other questions? So what are the nice things here? That, for example, you can see that it's related to k-means in that sense, that in k-means we also calculate the average in each cluster, right? You just take the average of those points that belong to one cluster, and that will be the updated mu. We do something similar here, but we use all the points with different weights. So it's like a weighted average of all sample points. In k-means, you just use the average of those points that belong to a cluster. That's one thing. The other thing we already discussed in the previous lecture, that if you do these EM steps, then the likelihood function is increasing or doesn't change. So we are increasing the likelihood function, like with maximum likelihood estimation you do, but there's no step size parameter that you need to tune. Right? So it's we calculate these updates, no step size parameters to tune, and still this iteration still increases the likelihood function.
Can you say the step size again?
So if you just if you do gradient ascent, you calculate the derivative, and then you need to tune a step size, how long you move to that direction. But here we don't have that. All right, so this is just the summary of what we do. So each step you calculate these probabilities. They were denoted with Rij. In the M step you update mu it using these probabilities. And you do this iteration, and we are done. So it's very simple to implement, and it increases your likelihood usually, or it doesn't decrease at least. All right, so what can we do if our problem is more general, that we don't even know the pi 1, pi 2, pi k quantities. We don't know the covariance matrices, sigma 1, sigma 2, sigma k, and we don't know mu 1, mu 2, mu k, and this could be general positive semi-definite matrices. So we do exactly the same thing. The only difference is the calculations will be slightly more complicated. So in this case, we want to learn parameter theta, which will be all the parameters, not just the mean parameters, but the pi's and the sigmas as well. We assume that we already, in time step t-1, we have these estimates. And we do the same thing. We create a Q function, same as before. We calculate the Rij quantities. They are same as before. And the only difference now is that when we do the M step, we do need to calculate this derivative with not only respect to the mu's, but with respect to the pi's and with respect to the sigmas. And if you do these calculations, you will see that you can solve all of them in closed form, and then you will get these updates.
So it's still decoupled?
Yeah, it still decouples and still a linear system, and you can still solve them. Okay. So the updates for the mu's will be exactly the same as before. The updates for the covariance matrices will be just the weighted average with those weights that we calculated of these quantities. So if this was a row vector, then so this is a column vector, and this is a row vector. So this is a matrix. And for the pi's, again, you just need to calculate the empirical average of these weights. So the E step is exactly the same. The M step is slightly more complicated, but you can calculate the derivatives, you can solve those linear systems, and you are done. Okay, so homework or midterm question to check if this is really hold. Any question? Right, so the nice thing that really at the end, so of course it was lots of calculations, we spent like 2 lectures on this, but at the end we have like 3 lines of equations. So it's pretty simple, and let's see how it works in practice. So we have 3 Gaussians. These are the sample points. Each circle is a sample point, and I want to show the update of the EM equations. These, the colors show pi1, pi2, pi3, so they sum to 1. And the center of these ellipsoids are the mean vectors, and the shape of these ellipsoids are just based on the structure of the covariance matrix. Okay, and this is how the update goes. That first iteration, we have these parameters, then this, and you can see how the posterior probabilities, they get more and more confident that these points belong to cluster green. And at the end, we find these ellipsoids. All right, and here is just another demonstration of the same thing. This was our data set, and I fit 1, 2, 3, 4, 5 Gaussians, and here you can see the 6 Gaussians, and here you can see those 6 Gaussians with the covariance structure, and this would be like the estimated density at the end. And of course, you can do this in higher dimension as well. It's just it's easier to show in 2D.
So you should again with random means, I guess, right? You randomize all the parameters you would like to estimate, like the price, means.
So everything is random, and I estimate all of those parameters.
So probably the solution is going to depend also on how you choose, how you seed them?
Yes, yes. So it's a local maximum likelihood estimation. So the final estimation depends on your seed parameters, and you might need to do some random restarts to get satisfactory results.
Perhaps multiple starts?
Yes, multiple starts. Yes?
How do you compare different number of Gaussians?
So instead of 5 or 6, you mean? That's a good point. So usually what people do, they introduce some penalization factor for the number of Gaussians, that you don't want to fit too many Gaussians because you might overfit the data. So in the extreme case, I could just say each dot is a Gaussian, right? So you penalize for the complexity, and there are many different ways how to do that. But that's what you do. So you don't want to let fit too complicated models. In this case, we just assume somehow magically we know how many we want to fit. Other questions? All right. So let's continue with, so that's for the EM and mixture of Gaussians. Let's continue with another unsupervised learning technique, and that will be the principal component analysis. So here we will do something different. Again, it's an unsupervised learning technique. We just have the data, no class labels. And we assume that the data is high dimensional, and somehow we want to reduce the dimension of the data. So there are many different applications. We will see some applications in data visualization, data compression, and noise reduction using PCA, or principal component analysis. And here is an example it's a motivating example, that we have a data set in a matrix form. So it's 53 blood and urine samples from 65 people. And then the question is, how can we visualize these measurements? Okay, so 53 blood and urine samples from 65 people. And somehow I want to visualize our data. So how would you do that?
How do you get more people than samples?
So we have so we have 53 people and 65 different features that I measure in a matrix form. I have this matrix, and somehow I want to visualize it to understand what's going on. So what should we do? Don't say do PCA, just something else.
Give some statistics.
Right, so we can see if we can see some statistical correlations between these points. For visualization, here is one example that we could do, that it's called spectral format. So for each person, I draw a curve. And then I will have 65 curves. So I have 53 features and 65 people. And 53 features. And one way to visualize that, one way to visualize this matrix here is, say this, that I have 53 features, and for each person I draw a curve, and then I can see at least that how these features are related to each other, but it's difficult to compare the different patients in this case.
What do you actually want to find out from this data?
I just want to understand how this data looks like. I want to understand.
Do you want to know if one of the people is different than the others?
Right, for example, that I want to know if people are different, or I want to know if, for example, if one feature is big, then the other feature will be also big. So somehow I just want to understand what's correlated with what in this data set.
You could probably run the box plots. So in this case, actually, I don't know why you, how would you order the features in the first place?
I just did randomly. Because I didn't have better ideas. But right, that's a good question how you would order. But anyhow, I'm just showing that there are 53 features, and these are the values of those different features. So another thing we could do that we could use this format as well, that for each feature, we could draw the value of this feature for each person. Right? So there are 65 people, and this person has this feature value. But again, then it's difficult to see the correlation between the features. So now I would have 53 pictures of like this. And then it's not so easy to see the correlation between the different features. Here is another thing we could do, that we could try to visualize the data in, say, 2 dimensions, that I choose 2 features, and I just plot where the people are in this feature space. And that's slightly better, because now I can see that how the different people and the different features relate to each other. But I can do that only for 2 features. I can go higher, like in 3D. I can choose 3 features and plot in a 3D place where the people are. But then I have difficulties how to go further, because I'm not that good showing 4 dimension in 2D space. All right, so with PCA, the question we study is whether there's a representation of these features that's somehow better than this coordinate axis, in that sense that I want to, say, visualize these features again in a 2D space in such a way that when I project my data to this 2D space, I lose the less information. So apparently when I plot my data in this 2D space, I lost lots of information because I lost information about the other features. But is there a transformation of the data such that when I plot this transformed data in a 2D space, I wouldn't lose much information? That's what we are going to study. Right? So for example, if there are strong correlation between these 53 dimensions, for example, the correlation could be so big that some features might have exactly the same values, then I know I wouldn't need to show those values, because I know exactly that they are the same for each feature. So the question we are going to study is how to find the smallest subspace in this 53-dimensional space that keeps the most information about the original data. Okay, and the solution for this problem will be the principal component analysis. So we will be looking for a subspace in this 53-dimensional space that keeps the most information about the data. The solution is, yes?
The smallest is easy to evaluate, but how do you define the most information?
Right, so we will discuss what I mean on most information in a sec. So what we will mean on that is after projection, you had a 53-dimensional vector, feature vector, and after projection you want to keep the most power of your data, in that sense that, for example, I'm in 2D and here is a data point. If I project to this axis, then this will be my projected data point, and this is the information that I lose. I want to minimize this lost information. Okay, so here is another example. If I have a data point here, I project this data point to this axis, then this would be my lost information. I will, for all of the data points, I will calculate how much information I lose when I do these projections, and I want to minimize this loss. Okay? All right, so again, I have a data set. Now we are just in 2D, x1 and x2. This is my data set. If I project this 2D data set to this 1D straight line, to this subspace, then these would be the projected points. new features. And this would be the information that I lose, and I want to minimize this loss.
Why should be the subspace linear?
That's a good question.
Can you just, if it's fine, just label the data?
So we don't have label. So okay, many questions. So I have unlabeled data set.
No, but I mean, you just move, you know, you just, if it passes not through the origin, then you just can take that vector and subtract it from the other one. Like a translation.
Right. So here is a data set. My goal is, as a very first goal, to find a straight line such that if I project the points to the straight line, I keep the most information about these points. Okay? And that will be my first goal. So this straight line doesn't need to cross the origin. So that's to answer your translation question. You ask why I want to project to a straight line, why I don't something nonlinear. And that's a good point, and many times you want to do that. We will start discussing straight line just because that's the simplest problem. But you are right. For example, if my data set looks like this, then I want to compress again this to the data set, I might want to project to something like this, right? But not to a straight line, because I would lose lots of information. So to start with something simple, we want to project the data points to a straight line, or in higher dimension to a subspace. But the subspace doesn't need to cross the origin. Such a way that we keep the most information. And on most information, what I mean, that if I project a point to this subspace, then I minimize this loss. Or equivalently, I can say if I project the points to this subspace, then in this subspace, the variance of the points is maximized. Okay, so to answer your question, what I mean to keep the most information is either to minimize this loss or to maximize the variance here. These are equivalent goals. Okay, so either I want to maximize the variance of the projected data, or equivalently I can say I want to minimize the mean square distance between the data point and the projections. All right, and if we do this, then this vector that points to this direction and has unit length is called the first principal component.
Why is it first? What?
Right. So if I want to project to a straight line, then I will just call that vector that points to the direction of the straight line as a first principal component. If I want to generalize...
Direction doesn't matter.
That doesn't matter. You can point to this direction as well. So it just has to be a unit vector of unit length, the direction that matters, either this way or that way. But if I want to project not just to a straight line, but I can generalize this to project to a subspace, then I can do this iteratively in that sense that first I just project to a straight line. That will be the first principal component vector. And then I can take the residual subspace and I can project to the first principal component on that residual subspace, and that will be my second principal component.
So do we also have a bias term in here then, since it's not intersecting with the origin?
No. So what I mean on that, I have this data set. I project the points to this data set. So what you mean on bias in this case?
Like, if you just had the principal components, then...
So I mean that the principal Okay, so let's simplify our life and let me assume that I got the data set and I subtract the mean of the data set. Okay, and from now on we will assume that the origin is the mean of the data points are in the origin of my coordinate system. Okay, so from now on that's our assumption.
So actually you do this iteratively,
Mm-hmm.
but it doesn't have to be the best way, right? Because it's like a greedy method.
It's a greedy method, and it's a question, is it the best way or not? Good point. It turns out that's the best way in this case. We will see why. Okay.
I wonder why the two goes equivalent, that is maximizing the variance is equal to minimizing loss.
Right, so that's another good question. And there are slides about this to prove that. And, so if we have time, we will discuss that. If not, please look at the slides and then you will see that. But that's not that trivial question, but I don't know, it's a few lines of proof. Yep.
You end up with an orthonormal basis of some subspace because you're always...
Yeah, so I will be looking for an orthonormal base, a new orthonormal basis. Okay, so for example, I have this two-dimensional Gaussian data set. First question, what is that subspace? So I already subtracted the mean, so this is the origin. What is that direction that maximizes the variance? If you project the data point, your variance of the projected data points will be maximum, and that's this direction. So that will be the first principal component on axis. The second principal component axis would be orthonormal to this, and there's only one orthonormal axis in 2D to this. But I can ask the same questions. For example, if I have 3D points, then this will be the first. So imagine that this is a 3D point cloud. This would be the first principal component. And then the second principal component would be in a space that's orthogonal to this straight line. And you do the same thing in that space. Okay, so this is formally what we do. That I already assumed that I have center data. I subtracted the mean. And this center data is x1, x2, xm. And my goal is to find that W1 vector, that direction, that maximizes the variance. In this case, the variance is just the square norm, that maximizes the variance of the projected points. So W is a vector with length 1. And what I need to do is to maximize the empirical average of the inner product between W and xi, and you square this. That's the direction that maximizes the variance. And that's the definition of the first principal component. Does it make sense? So you have instance xi. If I want to project x, so this is, okay. This is W1. This is the origin. This is xi. What is this vector here?
Projection of xi onto...
Right, so with mathematical equations. So this is xi, this is W1.
Linear product between W1 xi.
So, right, so that's xi transpose W1. This is a scalar. If I want to know this vector, that would be W1 times xi transpose W1. Right, so that's the projection. And and I want to maximize the variance of these projections. So I want to maximize the empirical average of these inner products squared. And we want to know what's that W1 vector. To find the second principal component analysis, we do this in the residual space. So I already know what's W1. So W1 transpose Xi is the length of this projection. W1 times W1 transpose Xi is that vector that points to the projected point. We call this PCA reconstruction vector because in the PCA space, which is PCA space now is just W1, this would be the projected point. We call this PCA reconstruction. And then Xi minus this is the residual error. To find the second PCA vector, you want to minimize the variance. Sorry, you want to maximize the variance of these residual errors. And you do this iteration again and again. So W2 will be that vector that maximizes this expression. Okay, so I try to illustrate this with this figure. So now we are in a 3D space. This is a instance X. If this is W1, then and the norm of W1 is 1, then this is W1 transpose X. That's the length. This vector is W1 times W1 transpose X. This green point is called PCA reconstruction. This is called reconstruction error. And to find the second PCA vector, I just need to calculate for all instances the x minus the reconstructed PCA vector, x minus x prime, and do the same thing here in this residual space, W2. All right, and to find k principal component vectors, you do this k times. So Wk will be, you maximize that vector which has unit length and maximizes the residual, the variance of the residual vectors of the k minus 1 principal directions. Okay? And then we are done. So that's the definition. And actually, it's already an algorithm, so if you can solve it. So now the question is how to solve it, right? How to solve these maximization problems, but assume that we know how to solve these maximization problems for a sec. By the way, okay, if we are here, so this is a maximization problem. I already know W1, W2, Wk minus 1. How would you solve this maximization problem? Right, so it's a quadratic cost function, and you can use Lagrange multipliers to force that the norm of W is 1. You calculate the derivatives, and you will have a linear system for that, and you are good. Here is the second algorithm, so that's algorithm 1. And here is a second algorithm which is equivalent with algorithm 1. And this is what you do. So given your centered data X, or doesn't even need to be centered in this case. So given your data set X1, X2, Xm, you compute the empirical covariance matrix sigma. So that's this, where X bar is just the empirical mean. You calculate this covariance matrix. And I claim that the first k eigenvectors of this sigma is exactly the first k vectors that you would found with this algorithm 1. It's not trivial to see, so you have to believe me for a sec, that if you find the k eigenvectors of sigma, first k eigenvectors of sigma, those are exactly these vectors that you would find with algorithm 1. Is the algorithm too clear? So you just calculate the empirical covariance matrix.
You're missing an I there, right? It's Xi.
Oh, there's an Xi here. Good point.
Which one is computationally more efficient?
In practice, people don't use this. They use this or the third algorithm that I will tell you. Okay, so this is just a pseudocode for algorithm 2. Right, so first, okay, so we didn't discuss one detail. So I just said that you find the eigenvectors of sigma. How would you find the eigenvectors of sigma? So I give you a covariance matrix. My question, what's the first eigenvector of that sigma? How would you give it? So you can do SVD, but for example, say you don't know SVD. Then you want, so you just want to design an algorithm that you can run and would give you the solution. Yeah, so the most easiest way is the power method, and this is what you would do. That sigma is your input. I want to find the first eigenvector of sigma, and you start from a random vector v, you calculate sigma times v, and then you normalize v to have unit norm, and you do this iteration. And that will be the first eigenvector of sigma. To calculate the second eigenvectors, you just need to do this in the residual space. So you already know the first principal component vector v. Then you calculate lambda scalar, which will be just this v transpose times the covariance matrix times v. This will be a scalar. You subtract this lambda times the first principal component vector times its transposed, and that will give you like a residual covariance matrix, and you can do the same power method in this residual covariance matrix, and that will give you the second PCA vector. So you want to subtract this. So when you do again the power method, then you want to converge to the second PCA vector.
You said you're just picking random v's?
You start from a random v,
And then you just iterate on
and then you do this iteration. Okay, so this is how it works in, I just did a MATLAB demonstration on this. So this is a point cloud, and this is the first principal component, second principal component, third principal component. I start from this random v, and just want to show that it, oops. So it's converging pretty fast to the first principal component. So like in 5 iterations, you are already there.
What's the convergence rate?
It's exponential. All right. So here is an algorithm 3. You have a data matrix x1, x2, xn, which is, say, each instance xi is capital N dimensional. So here is your data matrix X. This is capital N. We have M instances, and you do a singular value decomposition. So X will be U times S times V transpose, where U is an orthonormal matrix. So U transpose U is the identity matrix. V is again an orthonormal matrix. So V transpose V is an identity matrix, and S is a diagonal matrix. That's what you do with singular value decomposition. And you order the singular values such that this element is the biggest, this is the smallest. And then, if you want to find the first k principal component vectors, then you just choose the first k columns of U. And those will be your first k principal components. Okay, so this is algorithm 3. You do a single value decomposition, and you keep the first k columns of U.
I have a question about this power method. In the previous, it seems like the first principle corresponds to the eigenvector corresponds to the largest eigenvector
Of sigma.
of sigma, but this sigma is the covariance.
Is the covariance matrix of your
But
data.
it seems like you take the
That's sigma.
eigenvalue 1. If you start, can we go back go to 20 seconds now?
Which one?
Where you describe this power method.
The power, yep.
Power method. So V equals sigma V, so it's like...
It's converging to the largest eigenvector of sigma, this.
Then the largest eigenvalue is going to be 1. It
Mm.
seems like if, right, the V equals sigma V. Am I missing something like that?
So V is just the eigenvector,
Right.
right? If you want,
So you converge to the fixed point of this.
sure, you have,
So you will have then the limit is going to be eigenvector corresponding to eigenvalue 1.
there's no, so this will converge to that eigenvector that has the largest eigenvalue.
But that eigenvalue should be 1, I guess, because...
No, the eigenvalue will be this.
So in the limit, the limiting vector is not going to satisfy the same equation that you started with in the first place?
So you normalize V here to have a unit norm.
Okay, I have to check my stuff.
So you converge to a vector that has unit norm.
So
This
sigma is the covariance matrix, not the correlation matrix.
is a covariance matrix,
Not the correlation.
not a correlation matrix. Okay, so we have these 3 algorithms, and let's see some applications. So one application is where PCA was popular, is face recognition. So you have a data set of faces, and you want to identify a specific person from this data set. So you have this data set, and then I have a query image, and you want to know which person this query image belongs to. But the conditions might be, you might change the conditions, that the light might be different, and so on. Okay, so assume that each image is, say, 256 times 256. Okay? So then I can represent each image as a 65,000 dimensional feature vector, right? And so there are two, so each instance again is this huge 65,000 dimensional feature vector. And there are 2 methods that people use in practice. The method A is that for each person in this data set, you build a PCA subspace. So for example, you have 10 images of each person, or I don't know, maybe. Right, so let it be, I don't know, 100 images of each person. And then using that data set, for each person, you create a subspace. And when you have a query image, you check which subspace reconstruct the best that query image. And which subspace reconstruct the best that query image, we say that that's the winner, and that's the the query image belongs to that subspace and that person. Okay, is that clear? So for each person, you create a PCA subspace, and then you, for a query image, you check which subspace reconstruct that person the best.
How do you check which subspace reconstructs the...
So you project the query image to that subspace, and you check the residual error. Okay?
The smaller the better. The smaller the better. So
Yeah, the smaller the reconstruction error, the better it is.
it's almost like this.
So there's a method B that you just, and people use this as well, that you build just one PCA data base for the whole data set. So you start with the whole data set, you calculate the PCA vectors, and then you just use the weights in that new PCA coordinate system as your new features. And then you train a classification based on those features. So basically you have the big 65,000 dimensional feature data set. and you compress that, say, 200. You just select the first 200 principal components. Then you will have new 200-dimensional feature vectors, and you train a classifier with those 200-dimensional features.
You need the labels.
So each image was 65,000 dimensional. With PCA, you compress them, say, to 200. Okay, so you select the first 200 principal components. In that coordinate system, you will have 200 coordinates for each image. Those will be your new features. And now you have a new data set where the dimension is only 200. And then you can train a classifier.
But you need the labels.
Sure, you still have the same labels. So it's a classification problem. Yes.
So you assume you know which pictures in your training data.
In the training data belongs to which person. Yeah, so it's a classification problem, not a clustering problem.
With PCA, you can reduce dimensions, but it also comes with a cost. When you can't map it back, you are treating it as a black box. So how would you keep those information?
So in this case, you don't keep. You just care about. So it was a classification problem. You just care about whether you can solve this classification problem or not, right? So you compress. So the point is that you want to compress your feature vectors to a smaller dimensional space while keeping the most information. And we want to do that because in high dimensional spaces you can easily overfit. But if you compress your data to a smaller dimensional space while keeping most information, then you might get better classification accuracy. All right, so the issue is that, as we discussed, we have this huge, 64,000 dimensional feature vectors. Which means if I have m instances, each of them is 64,000 dimensional, I want to calculate the empirical covariance matrix. That will be 64,000 times 64,000. And then I need to calculate the eigenvectors of this huge matrix. That's just impossible. So we cannot do that. So what would you do? So you see the point, right? You calculate this sigma, x times x transpose. It's 64,000 times 64,000. And I need the eigenvectors of that. Say my data set, let's assume m was 100. What would you do?
Is this a sparse matrix?
No, it's just 64,000 times 100. Not sparse, nothing. I need the eigenvectors of sigma. If you solve it, you can leave.
Compute the eigenvector of x transpose times x.
Right, so x times x transpose is 64,000 times 64,000. We cannot do anything with that. But your suggestion is that instead of x times x transpose, let's work with x transpose x. It's just 100 times 100. But now the question is there any relationship between the eigenvectors and the eigenvalues of x transpose x and x times x transpose?
Yeah, eigenvalue is the same, but the eigenvector can be changed.
Right, so here's a statement that, so as you suggested, we will work with L, x transpose x, instead of sigma x times x transpose. And the statement is, if V is an eigenvector of L, and we can calculate V because it's just a 100 by 100 matrix, then x times V is an eigenvector of sigma. Okay, so if you calculate the eigenvectors of this 100 times 100 matrix, then you can calculate the eigenvectors of sigma. And you can prove that there's a one-to-one correspondence. So they have the same number of eigenvectors, and that's the relationship between those, that x times V is an eigenvector of sigma. And we will continue from here next time. Before you go, I just quickly tell the proof. It's just 5 lines. So you calculate L times V is gamma times V. L is X transpose X. And then you multiply this equation both from the left X. So we will have X times X transpose V is X times gamma times V. And because X times X transpose is sigma, we can see the sigma times X times V is gamma times X times V. So X times V is the eigenvector of sigma. That's simple.
Do you have any grasp on the relationship of the order of the eigenvalues?
So that's the same as well. So you, even though...
No, yeah, but I mean, in order. So my point is that gamma might be the biggest of L, but how does it correspond in like X? So, in sigma, sorry. So gamma might be the biggest eigen...
Then it will be the biggest for sigma as well.
So L has the biggest 100.
Yes. So, right.
So they both have the same eigenvalues, I guess, right? Or is it?
Yeah.
Eigenvalues are the same?
So they are a bit they are linearly so there's this relationship. So I cannot say they are
Eigenvectors
Oh, yeah,
are linearly
because-
translated, but eigenvalues
so you can
are the same. Eigenvalues are the same.
Yeah,
so it doesn't matter.
the rank of X transpose is most 100, so you're fine.
Right.
Yeah, sure.
Anyhow, so we will continue from here next time. So the lengths of these are not 1. That's why it's not gamma. But that doesn't matter.
PCA is still what they use.